Today's topic is Alfven wave. Alfven wave is low frequency wave produced in plasma by oscillations of ions in the presence of magnetic field. The ion mass density provides the inertia and the presence of magnetic field provides the restoring force. These waves propagate in the direction of magnetic field. These waves can change into the magnetosonic waves when the propagation is perpendicular to the direction of magnetic field. Frequency of Alfven wave is much smaller than the ion and electron cyclotron frequency. To obtain the dispersion relation, consider Maxwell's equations. Dispersion relation is the relation between omega and k. Relation between angular frequency omega and wave number k. We use these two Maxwell's equations. First is del cross E equal to minus delta B upon delta T, and second is C square del cross B equal to 4 pi J plus delta E upon delta T. Here in second Maxwell equation, we have transformed it. We can write this second Maxwell equation as curl B, that is del cross B, equal to mu 0 into J plus epsilon 0 delta E upon delta T. Mu 0 is with both J vector and mu 0 is also with epsilon 0 delta E upon delta T. Then with delta E upon delta T, we have mu 0 epsilon 0, and for mu 0 epsilon 0, we write 1 upon c square. If c is the velocity of light, then c is equal to 1 upon under root mu 0 epsilon 0. So for mu 0 epsilon 0, we write 1 upon c square. Similarly, in the first term, we have mu 0 j. We then multiply this term by epsilon 0 and divide by epsilon 0, and then write mu 0 epsilon 0 as 1 upon c square. So c square comes in both the right hand side terms. In the denominator, it is taken common and bring it to left hand side. So in left hand side, we have c square into del cross b. And then in first term, which was mu 0 j, we multiplied this by epsilon 0 and divide by epsilon 0 and write mu 0 epsilon 0 as 1 upon c square. And also we write in place of epsilon 0, we write 1 upon 4 pi. In this way, we get this second Maxwell equation for c square del cross b equal to 4 pi j plus delta E upon delta T. Assuming a small perturbation in parameters E vector, B vector and J vector H, we write E vector as E0 vector plus E1 vector, B vector equal to B0 vector plus B1 vector, and J vector as J0 vector plus J1 vector. These E0 vector, B0 vector and J0 vector are the equilibrium values of E vector, B vector and J vector, and these quantities E1 vector, B1 vector and J1 vector. These are small perturbations. These are small changes in their values. If we assume such a small perturbation, and assuming change in equilibrium values delta E0 is 0 and delta B0 is 0 and delta J0 is 0, we then have these two equations. If we substitute for E vector, B vector and J vector as E equal to E0 plus E1, B equal to B0 plus B1 and J equal to J0 plus J1, and assume that delta E0 is 0 and delta B0 is 0 and delta J0 is 0, then these two equations can be written as del cross E1 equal to minus delta B1 upon delta T and C square del cross B1 equal to 4 pi J1 plus delta E1 upon delta T. These two equations can be obtained directly from these two equations 1 and 2. Replace E by E1, B by B1 and J by J1. Now E1, B1 and J1 are the small changes in the values of E, B and J. We have now these two equations for E1 vector, B1 vector and J1 vector. Write these two equations as equations 3 and 4. Differentiating equation 2 with respect to T, we get, it is not equation 2, it is equation 4. So we differentiate equation 4 with respect to T and we get C square del cross delta upon delta T. This differentiation is operated before B1 and we get C square del cross delta B1 upon delta T equal to 4 pi delta upon delta T J1 plus d2 E1 upon dt square. So differentiating with respect to time t, this equation 4, we get this equation. Write this as equation 5. Now substituting the value of delta B1 upon delta T from equation 3 we have. From equation 3 we have delta B1 upon delta T equal to minus del cross E1 and we put this value of delta B1 upon delta T in this equation and get minus C square del cross E1. Here we have substituted for delta B1 upon delta T as minus del cross E1 and right hand side is 4 pi delta J1 upon delta T plus d2 E1 upon dt square. Now in this left hand side we have del vector cross E vector. Now we use the formula A vector cross B vector cross C vector and A vector cross B vector cross C vector is A dot C times B minus A dot B times C. So the first term is A dot C times B. It gives del vector dot E vector times del vector, and that del vector we written in left side and write as del vector del dot E. It is gradient of divergence E. In right side there is no meaning of del vector, so we write del vector in left side. So the first term comes from A dot C times B. A dot C is del vector dot E vector, and times del vector, we write this del vector to the left. Then next term is minus A dot B times C. So we have minus A dot B is del dot del, that is del square, and times C, that is E1 vector. So del cross E1 can be written as del of del vector dot E1 vector minus del square E1 vector, and we write right hand side as it is 4 pi delta J1 upon delta T plus d2 E1 upon dt square. If we assume plane wave solution as e to the power minus I omega t minus kx, then we have delta upon delta t as minus I omega. If we differentiate it with respect to t, we get minus I omega, because with t we have minus I omega. So delta upon delta t is equal to minus I omega, and if we differentiate with respect to x, then delta upon delta x will give ik, because with x we have ik. So delta upon delta t is minus I omega and delta upon delta x is ik. And for transverse oscillations, we write del vector dot E1 vector, which comes in first term of left hand side, del vector dot E1 vector. If we use for del vector as delta upon delta x, its x component, and delta upon delta x is ik. So this del vector dot E1 vector becomes ik vector dot E1 vector, and for transverse oscillations this is equal to 0, because for transverse oscillations k vector is perpendicular to E1 vector. Electric field oscillates in a direction perpendicular to the direction of propagation. Then from equation 6 we get the first term in left hand side is 0. Then the term remaining is plus c square del square E1. So it is c square, and del square E1 is written as minus k square E1, because delta upon delta x is ik. If we differentiate with x 2 times for d2 upon dx square, we will get ik into ik, that is minus k square. So in this del square, x component is d2 by dx square, and which is equal to minus k square. So we write for minus del square E1, for del square E1 as minus k square E1. So left hand side becomes minus c square k square E1 vector, and in right hand side we have minus 4 pi I omega j1, because for delta upon delta t we write minus I omega, and in the second term of right hand side, which is 2 times differentiation with respect to t, we get minus omega square E1, because delta upon delta t is minus I omega. So d2 by dt square is minus I omega into minus I omega, that is I square omega square, that is minus omega square. So this 2 times differentiation with t, dt by dt square is equal to minus omega square, and the second term in right hand side will becomes minus omega square E1 vector. In this way we get now this relation. Bring this term of E1 vector from right hand side to left hand side and take this E1 vector common. Then we get E1 vector into omega square minus c square k square equal to minus 4 pi I omega j1. This equation is known as wave equation for plasma. So this is the wave equation for plasma. E1 vector into omega square minus c square k square equal to minus 4 pi I omega j1 vector. We write this equation as equation 7. To obtain the complete dispersion relation, we have to substitute the value of j1 vector. J1 vector is current density for ions, and current density for ions J1 vector is from the formula NeV. We write N0eV1I because we write J1 is, so we write here for V1, and I is for ion because it is the current density for ions. And in place of N we write N0, it is the equilibrium density of ions. So current density from the formula J equal to NeV, so we write for current density for ions as J1 vector equal to N0eV1I. Here it is written as positive sign because ions are positively charged particles having charge plus E. For electrons we have to write minus NeV because electrons have charge minus E. So this is current density for ions. To evaluate the velocity V1 for ions V1I, we use the equation of motion for ion. Equation of motion for ion is this: mass into acceleration equal to force. Mass for ion is written as capital M. For mass of electron we write small m. So force on ion is mass into acceleration. Mass is capital N, m, and acceleration is dv1 upon dt. This v1 is v1I, velocity of ion, and this force is equal to E into E vector plus v1 vector cross b vector. Force on ion is due to electric field and magnetic field, and force due to electric field is E vector, and force due to magnetic field B is E into V cross B. E is the charge on ion, so this is the equation of motion for ions. Force equal to mass into acceleration, m into dv1 upon dt, and it is equal to E into capital E vector plus v1 vector cross b vector. Now we consider velocity in xy plane, that is v1 vector is vxi plus vyj. We assume electric field along the direction of x-axis and write E vector as exi, and magnetic field along the direction of z-axis and write it as B vector equal to B0 k cap. So we assume electric field in the direction of x-axis and E vector is exi. Magnetic field is along the direction of z-axis and write B vector equal to B0 k cap. Velocity is in xy plane and we write velocity v1 vector equal to vxi plus vyj. Put all these values in this equation of motion for ion, and we get two equations for x and y components. In left hand side x component is m into minus I omega into Vx. Minus I omega is for d upon dt, differentiation with t. And in right hand side we have x component as e into ex plus vy b0. Ex is the x component of E vector and Vy b0 is x component of V1 vector cross B vector. Similarly, for y components we write capital M into minus I omega Vy equal to minus E Vx b0. For this y components in right hand side, y component of E vector is 0 because E vector is along the direction of x-axis. E vector is Exi cap. So y component for electric field E vector is 0 and y component for B1 vector cross B vector is minus Vx b0. These x and y component of V1 vector cross B vector can be determined by using a determinant. V1 vector cross B vector will be equal to a determinant having first row as I cap, j cap, k cap. Second row it have components of V1 vector that are Bx, By and 0. And in third row we have components of B vector that are 0, 0, B because B vector is along the direction of z-axis. In this way, by solving this determinant, we can find the components of V1 vector cross B vector, its x components and y components, x component as Vy b0 and y component as minus Vx b0. In this way, this equation of motion for ions is converted into its x and y components. We write these two equations as equations 10 and 11. Now from equation 11, we find the value of Vy, that is E Vx b0 upon I omega m, and now we write E b0 upon m as omega I. Here we write omega I equal to E b0 upon m, and it is cyclotron frequency for ions. Cyclotron frequency for ions is E b0 upon m. So here we find this term E b0 upon capital M and we write it as omega I. I for ion and omega is cyclotron frequency. So omega I is cyclotron frequency for ion. Now we get the value of Vy by this second equation and put this value of Vy into first equation so that we get the value of Vx. Substituting this value of Vy in equation 10, we have m into minus I omega Vx equal to E into Ex plus omega I Vx upon I omega b0 equal to E Ex plus E omega I b0 upon I omega Vx. So we have substituted in this equation the value of Vy equal to omega I Vx upon I omega and get this relation, and by using this relation we will find the value of Vx. So in right hand side now we have two terms. First is Eex and second is E omega I b0 upon I omega Vx. in left hand side we have capital M into minus I omega Vx. So Vx can be determined. We eliminate all other things except Vx in left hand side. So we divide each side by minus I omega M. Then Vx becomes Ex upon capital M into minus I omega plus E omega I B0 upon I omega capital M into minus I omega. We are dividing by capital M into minus I omega, which is in this left hand side, to get the value of Vx. Now the right hand side becomes Ex upon minus I omega M, and the second term in right hand side, which is small e omega I B0 upon I square omega square M, and we write for I square as minus 1. Minus sign is already, and I square is minus 1, so this term becomes positive and equal to E omega I B0 upon omega square M into Vx. Again the term E B0 upon M appears here. We again write it as omega I. So omega I appears 2 times, it is omega I square, and this second term will become omega I square upon omega square into Vx. Bring this term, second term having Vx into left hand side. Take Vx as common, and we have Vx into 1 minus omega I square upon omega square equal to Ex upon minus I omega M, or Vx equal to Ex upon minus I omega M into 1 minus omega I square upon omega square to the power minus 1. This is now the expression for Vx. From equations 7 and 8, from equations 7 and 8 we have Ex into omega square minus c square k square. These are not equations 7 and 8. Correct this. Ex into omega square minus c square is this equation. It is the equation 7. E1 vector into omega square minus c square k square equal to minus 4 pi I omega j1. In this equation 7, we have to put the value of j1, and value of j1 is n0 e v1I. So we write its x component. X component of equation 7. This is equation 7. We write its x component. We write in place of E1 vector as Ex, and for J1 vector as Jx. So x component of this equation will be Ex into omega square minus c square k square in left hand side, and in right hand side we have minus 4 pi I omega Jx. And Jx is from the formula NEV, it is N0 EVXI. It is the x component of current density N0 E Vxi. I is for ions. And for Vxi, we put this value of Vx because it is the x component of velocity for ion. So for Vxi, we write this value of Vx, that is Eex upon minus I omega m into 1 minus omega I square upon omega square to the power minus 1. So that the right hand side now becomes minus 4 pi I omega N0 E, and this is the value of Vxi. Now I is cancelled out in numerator and denominator. Minus sign is also cancelled out. Omega is also cancelled out. And we get 4 pi N0 E square upon capital M into 1 minus omega I square upon omega square to the power minus 1. And since the frequency of oscillations of ions in plasma, which is omega, it is much less than ion cyclotron frequency. So we have ion cyclotron frequency omega I much greater than omega. So we have omega I square upon omega square much greater than 1. So in this term inside the bracket, we can assume 1 as negligible quantity and we neglect it, and minus omega I square upon omega square to the power minus 1 will give minus omega square upon omega I square. Now put the value of omega I. Omega I is EB0 upon m. We get this term for omega square minus c square k square. It is equal to minus 4 pi N0 E square upon m omega square m square upon E square B0 square. Some terms are cancelled out. Remaining term in right hand side is minus 4 pi N0 omega square m upon B0 square. Bring this term into left hand side and take omega square common, and this term minus c square k square which is in left hand side, bring this to right hand side, and we get omega square into 1 plus 4 pi N0 m upon B0 square equal to c square k square, or omega square upon c square k square equal to 1 upon 1 plus 4 pi N0 m upon B0 square. Now write N0 capital M as rho. It is the density of ions. N0 is number of ions per unit volume and capital M is mass of each ion. So N0 capital M is the mass per unit volume. It is the density of ion. We write it by rho. So we have omega square upon c square k square equal to 1 upon 1 plus 4 pi rho upon B0 square. Now this quantity 4 pi rho upon B0 square is much greater than 1. So we neglect 1 in denominator, and the remaining term in right hand side will become B0 square upon 4 pi rho. Now omega square upon k square becomes c square B0 square upon 4 pi rho, or omega upon k becomes c B0 upon under root 4 pi rho. This omega upon k is velocity. We write it as VA. It is known as Alfven velocity. It is the velocity of Alfven wave, and velocity of Alfven wave VA is equal to c B0 upon under root 4 pi rho. This is the expression for Alfven velocity. It is the velocity of waves produced by oscillations of ions in the presence of magnetic field, in the direction of magnetic field.